I hate to do this to all of you. Let me flip through the next 2 or 3 slides. Okay. I can see where we're about to get to today. So we need to connect this back to the last chapter somehow. The last chapter was all about electric fields. It turns out that these things are not separate or distinct. They're sort of like different ways of looking at the exact same problem. Just like there were problems in Physics 220 that you could analyze with forces, and you could maybe look at the exact same problem in terms of potential and kinetic energy, okay? 2 ways of looking at the same thing, but there are connections between them. So any given problem, if there's an electric field that's there are going to be places that have high potential and places that have low potential inside of that electric field. So we have graphed this here real quickly. This is the exact same situation we had before, right? Positive here, negative here, an electric field going this way. We know that on this side we have high potential, because again it's defined on what a positive charge would do, and then the potential goes down as we approach the other side, and you can imagine eventually the charge is going to sit against this. Regions of space there have no potential because a charge would have no potential energy remaining. If we were to graph that, and this is meant to line up directly with what you see above, okay? I don't think it does because it's pretty close. I don't know that I copied it perfectly. So this corresponds to this side, and over here we're looking at that plate, okay? We start with some value of potential, and it's as high as it's ever going to be over on this side, and the amount of electric potential I have linearly decreases until I get to 0 over at the other side, okay? In this particular case, we're dealing with a constant electric field, and we can see how the potential varies as we move to different points in the electric field. It's a linear decrease. If I were to write this as an equation, it turns out that the electric field corresponds to the negative slope of the potential, or the negative change in potential with respect to, let's write this as L. This is basically a distance or a displacement. Now let's write it as distance, since that's what they did at the bottom there. Notice, potential versus distance, there's a slope, a rate of change. That's what this equation is giving us. The negative says it's a negative slope, okay? This tells us how the potential changes in an electric field. Question?
Does the observation that whenever we're trying to observe this kind of scenario where you're using a proton carry over to this as well?
Yeah. Okay. All of these equations are set up based on the proton. Everything gets flipped exactly reverse if an electron's in play. Okay? It's all based on what a proton would do. So I can take this equation, and again, keep in mind, it's the negative slope of the potential. The electric field is the negative slope of the potential. And we can rearrange this into an integral. And we're going to do that on the next slide. I'm going to go straight over here. And all I'm going to do is rearrange this and solve for the potential difference instead. It's equal to negative the integral of E dot dl from point A to point B. So we have 2 relationships that connect the electric field to a potential difference. If you're looking for the potential difference, you can start with the electric field and use this integral to get to it. On the other hand, if you happen to know something about the potential difference, you can use this to solve for the electric field in a given region of space, okay? And we're going to do an example with this in just a second. In fact, like almost right now, I just want to point out one thing here. This gives us some alternate units for electric field. Taking a look at this equation, in the numerator I have volts, and in the denominator it's just a distance, so it's meters, okay? Previously the electric field was newtons per coulomb. It can also be volts per meter, This can also be volts per meter. Either one of those is equally valid. So let me show you a little something about how this works. We're going to go forward 2 slides, and we have an example of this relationship between the potential and the electric field. So in this particular case, you can see we have a spherical conductor. So imagine a conductor, we've put some charge on it. All of that charge will be on the outside. We've learned how that works, which means that the electric field will look like this. If I put a positive charge anywhere near it, it's going to be pushed away radially outward. We have learned how to take a situation like this and use Gauss's law to get an equation for the electric field. We learned it looks exactly like what you get for a point charge. So I'm going to go ahead and just write that result down. And again, this comes from Gauss's law in the last chapter. So the electric field, specifically outside this conductor. What's the electric field inside? 0, right? In the conductor will be 0. So the electric field outside is going to be 1 over 4 pi epsilon naught times Q, the total amount of charge that's on the surface, divided by r squared, which is our distance away from the center of the conductor. And you can also write that as kq over r squared if you like that notation better. There have been a few questions about that. K is the exact same thing as 1 over 4 pi epsilon naught. Just depends on which terminology you prefer. You're probably thinking, K. K is easier to remember. It's one thing. Well, true. But there are problems sometimes where having the 4 pi epsilon naught lets you cancel some of it out, and it gets even simpler than K, so either one is perfectly okay. So, okay. Did you catch that? I heard it. I don't know if you did. Either one, K or not K, is okay. I need to go home. That's all there is to it. So, delta V is equal to VB minus VA, and we just learned it's equal to negative this integral from A to B E dot dl. Notice my integral this time, a couple of things. This is a path integral. This dl is a little segment along a certain route that we're going to take. It goes from a point over to another point. It's a path integral, not a surface integral. Also, we have a dot product in there. You might remember the dot product is something like this. It's the magnitude of both times the cosine of the angle between them. It essentially means that we're going to go along a certain direction, and we're only going to use the electric field components that are parallel to that direction, okay? So in this particular case, take a look over on the left-hand side. We are going to integrate from one point outside my conductor over to another point outside the conductor, okay? Essentially right along one of the electric field lines is perfectly fine. So you can imagine that if I'm looking at DL, which is a little piece of the path between point A and B, at all points, it points in the exact same direction as the electric field. So this dot product E dl cosine theta, well, the cosine theta is just going to be 1, and this is just going to be E times dl, okay? So let's go ahead and simplify that just a little bit. Ooh, let's rewrite this. Oops, that's the pointer thingy. Go away. So this is just going to be minus A to B E dl. Okay? Again, I can make that simplification because E and dl point in the same direction. We have an equation right above for the electric field in this region of space. So I'm going to take it and plug it in. So that means now we have delta V is equal to minus integral from point A to point B, 1 over 4 pi epsilon naught times Q over r squared. And I'm going to change the dl to dr. What's the r direction? Well, it just is along the radius pointing outward. That's the same as the L direction in this particular case. looking at that, the Q and the 4 pi epsilon naught are all constants. So I can pull those out of the integral. And now I've got minus Q over 4 pi epsilon naught integral a to b 1 over r squared dr. And that's an integral you should be able to do. So let's write that out again. And let's see, that's going to give me something like this, negative 1 over r. And we're going to evaluate that from RA to RB. So point A is distance RA away from the center, point B is distance RB from the center. So let's go to the next step. Let's see, now I've got minus Q over 4 pi epsilon naught. And then inside here, we're going to have minus 1 over RB minus a minus, so that'll give me a plus 1 over RA. And then I'm going to pull this negative sign inside here just to simplify a little bit. So that's going to be Q over 4 pi epsilon naught. And then we're going to have 1 over RB minus 1 over RA. Let's take a deep breath and see if you have a question. By the way, here in just a little bit, I'm going to give you a problem to work again so you don't have to listen to me talk for 75 minutes. Because I know it's exhausting. I don't like to hear myself talk for 75 minutes. Does anybody see anything up there that's a little confusing or part of those calculations that don't make sense? We are using a known electric field in our equation to sort of convert it over into a potential difference using this connection between these two concepts. Now, I'm going to make a quick simplification. We are going to let RB go very far away. We're going to let RB go very far away. So we're going to go from a point relatively close, RA, to some point that's very far away from my conductor, okay? Remember, if I get very far away from any charges, then at that point, we could say that the potential at point B is 0, okay? Far, far away from any charges, the potential at that location is going to be 0. So remember that on the left-hand side of this equation, I have VB minus VA, which is delta V. So VB is going to be 0, and RB is infinity, so that's 1 over infinity, so that term is going to be 0. And then I've got a negative sign on both sides, so those will cancel out. And we can say that the potential at point A, which is just some point outside the conductor, any point outside the conductor, some distance away, is equal to, let's see, Q over 4 pi epsilon naught R A. So if you are some distance on the outside, whatever that distance may be, okay, you can find a value for the potential at that location near some conductor that has a charge Q on it. Of course, if I make RA get big enough, right, if I get very, very far away, this gets larger. As I get farther away, the potential is dropping. So if I get an infinite distance away, then the potential for that point would be 0 as well. Okay? Let's see. Good. Got more slide on the next place. There are 2 more parts to this that we're going to do really quick. That's the long part. All right? Let's go over to this and say, let's find the value for the potential at the surface of the conductor. So in other words, we're going to say that R is equal to R0. If you go back and look at the diagram, they labeled the radius of the conductor as R0, so we'll just say that R is equal to R0. Don't think about this too hard. We just found the equation. V is 1 over 4 pi epsilon naught Q over, last time it was RA. Well, now I'm just going to let that be R0, which means it's 1 over 4 pi epsilon naught Q over R0. I'm not sure why that was even a problem. Agreed? Don't you wish they were all like that? We're just picking a value for R and plugging it in. And then finally, find V at a point inside the conductor. Any thoughts? It's a quick answer. Not as quick as you might be thinking, but quick. So in other words, we're looking for a place where R is less than R0. Keep in mind that in a conducting material, the electric field is equal to 0. If the electric field is equal to 0, then we can also say that delta V is equal to 0. Delta V is equal to 0. And that's between the surface and any point inside. If the change in potential or the difference in potential between the surface and any point inside is 0, well, that just means that this answer applies everywhere inside. V is equal to 1 over 4 pi epsilon naught Q over R, where R is less than R0. I like parts B and C of this problem because, well, the answers come kind of quickly. Let me label these B, C. I'll go back over here and call this A. So take a look at the graphs over on the right. Electric field and potential at different distances from the middle. We can see the graphs of the things we just found. So first of all, notice that the potential decreases as 1 over R as I get farther away. This whole thing is proportional to 1 over R. So the biggest it's ever going to get is when I'm really, really close, right at the surface, and it turns out it has that exact value everywhere inside, and then it falls off proportional to 1 over R as I get farther and farther away. That's what the potential is doing. The electric field, on the other hand, remember our electric field equation is proportional to 1 over R squared. And we saw that right there at the top on this slide, right? 1 over 4 pi epsilon naught Q over R squared. So we know as we get farther and farther away from the surface, the electric field is decreasing according to 1 over R squared, but the electric field inside is nothing. So you can see this drops immediately to 0, and everywhere inside the conductor, there's no electric field at all, even though there is a potential at all those points, okay? So we see something here about the relationship between the potential and the electric field. Does anybody have any questions before I ask you a few of these multiple choice questions and then give you a problem to work? I'm going to give you another Gauss's law problem because I've just seen the looks on your face, the love that you have for Gauss's law. Like some of you have already had the word Gauss like tattooed on various limbs, you know, because you're just like, oh, Gauss's law. Just so in love with this whole idea. I understand. I have 6 Gauss's law tattoos. Yeah. No. Okay, next slide. Next slide. I'll give you a second to think about it. What do you think? You have a question?
Yes.
Yes.
So, just to clarify, the potential of a conductor is equal and opposite on the inside than what it is on the surface.
Equal and opposite?
Yeah, so what I'm not understanding is because the overall difference in potential is zero.
This is the difference in potential between this point right at the surface and any point on the inside. So the difference is zero, which means it doesn't change. It's a constant value.
Okay.
Okay? Anybody have any votes here? It says 1, 2, 3, 4, 6. The answer there is 1. If you just think about it as how much opposition you're going to face, if I try to take this positive charge and push it this way, well, that's going to be harder than trying to push it any other direction because I'm going sort of directly upstream, right? It feels a force from the electric field this way, and I'm going to be directly opposing that. So that's going to take the most work from me to try to move it in that direction. But there is a direction where perhaps it is zero work. I don't know why there's a box over there on the left. That's kind of strange. A strange remnant of something. 1, 2, 3, 4, 5. Think about what happens if I go, first of all, here we determined I'm fighting against the force, against the electric field. That's going to be the most work. If I go this way, well, actually the electric field is helping me. That's going to be like the easiest in some ways. It's like, oh, I'm not really having to do anything. It's like moving itself. Here, I'm kind of going sort of like against, but not fully against the force that's fighting against me. Here, I'm not working against the force at all. I'm going perpendicular to the force. So in that particular case, I'm not doing any work trying to move the charge from point P over to 3, okay? And that is the last of those, which means it's time for me to give you all a problem. Does anybody have any questions about today's stuff before we revisit Gauss's law once more? No? All right, so okay, good afternoon, everybody. How are you? Where is everybody? This class just keeps getting smaller and smaller. What is happening? Are they getting scared? Extra credit for being here. Yeah, that does make a lot of sense. I'm really feeling what you're saying right now. Yeah. Extra credit for you all. Or we should send out an announcement telling like everyone that the exam is moved, you know, except only the people who are here will know that it's actually not. That'd be terrible, wouldn't it?
Send out an announcement with the answers to the quiz today.
The answers to the quiz today. Well, that doesn't really benefit you guys at all. You know, it just makes the other people freak out an awful lot. Huh. I don't know. We'll think. I feel like there should be at least a small prank on the other people. Yeah.
So you guys have a review session at the Catskills on Thursday.
Yeah. What if maybe the exam first page for just them is a drop form? Just the front page, that's it, drop. And then all of you, you know, like the ones who are normally here, I'll be sure not to give you that exam. And then they'll be freaked out a little bit. Yeah. And the rest of the pages are just blank. There's nothing else there. Just a drop form. Ideas. I'll think about this. So our exam is next Thursday. We've got a week and 2 days. So I think all of us need to just ponder that fact and how somewhat, I can tell you're disturbed. You're already in prayer or something. I'm not sure what's happening back there. So a couple of things that I want to say about that. First of all, we are wrapping up our 3rd chapter. So I get these chapter numbers confused. 22, 23, and 24,
Yeah.
I think are the right chapters. They've changed the chapter numbers or something, and things are confusing. So this chapter on electric potential will be the last chapter that we have covered on this first exam. That's not to say that, excuse me, I think I need to move. This, a lot of people are deciding to come through there, which is fine. That's not to say that we won't cover additional material before the exam. I'm going to see how that kind of works out because we might need the time. But I want to make sure that you have all the material that's going to be on the exam like a week in advance, okay, before, instead of presenting new things that are on there. So I'm thinking that we might actually be able to finish chapter 23 today or come really close, so it might dip into Thursday just a tad. After that, I would like to take some significant time to review and do practice problems and that sort of thing in class, and I need your help for that. So if there are topics that you're just like, please explain that again, send me an email that says, please explain this again, and I'll try to take time to do that. If there's a problem that you'd like to see worked again, or a homework problem that you're like, I need to know how to do this, or just some other random problem in the text that you think might be important, maybe it's an example or something, you're just like, please show us how to do this. I will take your emails and try to assemble probably about a class and a half, if not 2 full class sessions of just repeatedly going through things from chapter 22, 23, and 24, okay? So the sooner you send those emails, the more likely it would be that I can actually work those in. If you send me an email 10 minutes before class, I'm sorry. That's probably just not going to happen because I need a little bit of time to prepare, okay? So let's see here. Things closed down, so we need this file. That's what we're looking for. Good, everything is back. This means that the exam is going to break down really quite nice as far as the materials that we have are going to be like highly connected to each other. On the syllabus, it says we're supposed to do 1 more chapter before the exam that we're not going to do. And we kind of, I don't know, it's kind of off the reservation just a little bit. It's out to the side. It doesn't really connect with those first 3 chapters as well. If you really think about what we've been talking about, we dealt with force, field, and potential. Those will be the 3 big things that you're going to have to focus on for the first exam. Force, field, and potential. Okay? We are going to talk most of today about potential, although some of it is still going to connect back to electric field. I really hope that some of the graphics that we have today starts to give you a feel for how electric field and electric potential are all intertwined and connected, and you can't really separate them. So I'm going to take a good bit of time sort of explaining those diagrams and letting you try to absorb them, but that's later in today's class. So first of all, I want to do what is a relatively basic example dealing with potential. And I'm sorry that's a little hard to read. It says that there are 2 large parallel metal plates carrying opposite charges of equal magnitude. So I'm just going to draw sort of a side view of this and say that these are 2 large metal plates of equal magnitude but opposite charges. So we're saying that one of these is positively charged, one of these is negatively charged, and this creates an electric field in between that looks something like this. Because if I drop a positive charge anywhere between those 2 plates, it's going to be pushed away from the top plate and down toward the bottom plate. That defines the direction of the electric field. Notice it says they are separated by a distance of 45 millimeters. So we're going to say that this distance is 45 millimeters. And the potential difference between them is 350 volts. So we could say between these 2 points, we have a delta V, a potential difference of 350 volts. As a bit of a refresher, remember what this means. When we're talking about potential differences, we are saying that regions, let's say sort of up here near this plate, have high potential. There's a lot of reason for a positive charge dropped in that region to move. Just like if I take a mass, up here is a higher potential than near the ground, okay? Because there's going to be more potential energy in that region if I put a charge there. So this is where I have high potential, and this is where we have, down here is lower potential. from the standpoint of a positive charge, which is how we define all of these things. Now keep in mind, it's not like the way I've drawn it where just the top is high and just the bottom is low. It's like a gradient, okay? It's a slope. It's ever changing as we go from the highest possible potential and then to a little lower, 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 until the lowest possible potential at the bottom plate, okay? So a few different things we're going to ask, and I'm sorry that these questions aren't up here. I'm just going to go ahead and write them. So part A, find the magnitude of the electric field between the plates. And the problem also says that it will be a constant value. The value is constant. Find the magnitude of the electric field between the plates. If you take a look back in your notes from last week, you might find an equation that will allow us to get to this relatively quickly. There's an integral equation that we don't have to use here because the electric field is constant value, but you could maybe take that integral equation and look at a more simplified version and tell me what you see. Does anybody happen to see an equation in there that relates the electric field and the potential difference? Anybody? If you think you see something, shout it out. It's just something divided by something else. Yeah. If I'm just looking at the magnitude, it is the potential difference divided by the distance over which that potential difference is occurring. Remember, it's the slope. The electric field is essentially the slope of the potential. Okay? Specifically, if we weren't looking at the magnitude, it would be the negative slope. All right? So in this particular case, this is a relatively easy calculation. We've got 350, and I need to convert that millimeters into meters, so that's 0.045 in the denominator. You should get 7778. And you can express that two different ways. We have two different sets of units for the electric field. I could use what's here. We've got volts in the numerator and meters in the denominator, and that is perfectly good. Newtons per coulomb is also a unit that would work. Part A, you like part A, right? Part A is good. You can do part A. Part A is pretty happy. Part B, it's not going to get any worse. Next thing, we're going to find the magnitude of the force on a charge of Q equal to 2.9 nanocoulombs. So we're going to take a charge and put it in this region of electric field and see what force it experiences. How do we find the force from the electric field? F is equal to what? Careful. Connected to the electric field. That's the value we have. I'm hearing the equation for like the electric field created by a point charge, is what I think I was hearing. How is the force related to the electric field? Something times something.
Charge times the field.
Yeah, it's just the charge times the field. F is equal to QE. So I know the electric field that already exists. I'm going to drop a charge in there and see what force it experiences. So 2.9 nanocoulombs is 2.9 times 10 to the minus 9 coulombs. And the electric field is 7778. And that gets everything in consistent units. And when you multiply those, you will get newtons. You should get 2.26 times 10 to the minus 5 newtons of force on the charge in that region of space. Which brings me to part, let me read this and see which way I want to do this. Let's see, part C. Let's find the work done on the charge. We'll say done on Q. as it moves from the top plate to the bottom plate. I'm running out of space down there, aren't I? So we're going to have to go to the top to answer this, and I'm going to go the long way around. Yeah, this is completely pointless. There we go. Just to amuse myself. Okay? Find the work done on the charge as it moves from the top plate to the bottom. So we're going to pretend that we take this charge and drop it right next to the top plate, and that electric force is going to make it move to the bottom plate. And we're going to find out how much work is done. So you might remember that work just in general is equal to F times D. Yeah, exactly. Assuming that those are pointing in the same direction. If they're pointing different directions, there's also a cosine of the angle between them that you have to deal with. So in this particular case, it's just F times D, and we know the force is 2.26 times 10 to the minus 5, and D is 0.045 meters, once again. You should get 1.02 times 10 to the minus 6, and what are the units of work? Joules. Good. Units of work are joules. This is the work that's being done by the electric force to move the charge. Okay? One other thing that we can quickly find here is, let's see, find the change in electric potential energy. So find the change in potential energy from top to bottom. So again, this is the potential energy that the charge possesses. Remember, potential energy is possessed by the charge. Potential is something that points in space have. Okay? So we can find the change in potential energy by using an equation from last week. Let's see, so delta PE, or delta U is the same thing, is equal to the change in the potential times Q. The change in potential times Q. The change in potential is just 350, and Q is 2.9 times 10 to the minus 9 coulombs. Or you didn't even have to do that, because we already had the answer. You might remember that the change in potential energy is also equal to the work. Okay? So this is another way of coming at the same answer. For that, you should still get 1.02 times 10 to the minus 6 joules. The amount of work that's done is equal to the amount that the potential energy of the charge changes. Okay? And you can punch that in and see that you get the exact same thing. Does anybody have any questions on this particular example? Yeah.
I might have just missed this entirely. What is the units for potential difference?
Volts.
So then, because of the fact that it's force times distance, it's in meters and volts.
Volt times Coulomb results in joules.
So both numbers know.
Yeah.
Okay.
Anyone else? Okay. Moving forward. You might remember from last semester, and we're not going to dwell on this too much. I will do a quick example. I just want to point out that what we're doing now still ties into things you learned in 220, like conservation of energy. You might have remembered you had something like kinetic energy plus potential energy initial was equal to kinetic energy, and I'm writing that different than maybe you've seen it, final plus potential energy final, right? The amount of kinetic and potential energy that you have has to stay constant. It just changes forms. And we can use this equation as long as there are no non-conservative forces that are sort of taking energy away. So let me clarify this. This is for no non-conservative forces. Okay? And you may have learned last semester about a few different types of kinetic energy. There was like translational kinetic energy, which is 1/2 mv squared. And maybe you learned about rotational, which was 1/2 I omega squared. Does any of these equations look familiar at all? You've seen these before, okay? You might have learned about a few types of potential energy, like gravitational potential energy was M times G times Y. Spring potential energy, 1/2 kx squared. I can't remember if maybe you learned about any more. That was probably about it. And sometimes you had problems where you had to like mix all these together and figure out what types of kinetic and potential energy you had and solve for some unknown in there. I want to point out that at this point, this potential energy that we just learned about can be added to this list. So electric potential energy, which is equal to the potential difference times Q. And that should be a V, even though I kind of rounded it off a little bit. You get the idea. Or if we wanted to specify, say, at a single point, and keep in mind when we're doing conservation of energy, it's usually like how much do you have at this point, and then how much do you have at this other point. We might re-express this as, say, just U electric is equal to the potential at that point times Q instead of a difference in potential. So we're able to add to this list of things that you were already working with last semester, and we can do conservation of energy using electric potential energy. In 2 slides, I want to do a quick example that shows you how that works, and it's really straightforward and easy, okay? But first of all, let's take a look at this problem. Again, we've got this apparatus where we have a positively charged plate and a negatively charged plate. We have an electric field in between that points from positive to negative. This is saying that we take a proton and put it right next to the positive plate. We know it's going to get pushed this way. We're going to take an electron and put it right next to the other plate and release it. Okay? So we know that they're going to be pushed opposite directions and fly to the opposite plate. When they strike the opposite plate, which one has more kinetic energy? Which one would have more kinetic energy? What are you going to do? Any thoughts? You can vote with your fingers maybe if you think you have an answer.
Both not the same.
Both have the same. Why?
Because kinetic energy is supposed to be equal on both sides.
Close. You're right. Your answer is right. They have the same kinetic energy when they get to the other side. And what is the reason why?
Because initial is equal to final.
Initial is equal to final. Yeah, it basically goes back to this equation, right? They both start with the same amount of potential energy because a proton and electron have the same charge, and they're dealing with the same potential difference. So if they start with the same potential energy and lose all that potential energy as it gets converted to kinetic energy, they have to have the same kinetic energy at the end, okay? So we could say that both have the same initial potential energy. So that would be UI. This is all converted to kinetic energy. And if they start with the same and all of it gets converted, that means they're going to have the same K final. All the initial gets converted to kinetic energy. Okay? So let's do a quick problem related to conservation of energy, and then we're going to jump into what I really want to focus on today. Okay? So let's see. Here we have another problem where you can't read the top line. Beautiful, right? Hopefully you have it in front of you somewhere. It says that there is a small particle that has a charge negative 4.1 microcoulombs and a certain mass, it moves from point A, where the electric potential is one value, to point B, where the electric potential is another value. The electric force is the only force acting on this particle, and it has a speed that's given there at point A. So the fact that it says the electric force is the only force acting means I don't have to worry about gravitational potential energy or any other weird thing that's involved. I just have electrical stuff that we're focused on, okay? And we have two different points, so let's just go ahead and write these out. Here at point A, and here's a different point B. You could think of these as the initial and the final point when I'm dealing with conservation of energy. So I'm going to write down K at point A plus U at point A equals K at point B plus U at point B. And let's see, they told us at this point, at point A, the velocity at point A is 3.9 meters per second. And this is very quickly going to get confusing because we have velocity and potential, and both of them are V's. So let's be a little careful here. I'm going to make this V like smaller, maybe kind of cursive, just to keep track of things. So we also have a potential at point A that is, let's see, 190. And then we have a potential over here at point B that is 620. We are going to try to find the velocity at point B, the velocity at point B. So let's see what happens. At point A, kinetic energy, 1/2 mass times the velocity at point A squared. It has electric potential energy, and that's equal to, whoops, that's going to be plus Q times the potential at point A. And then at point B, we're going to have 1/2 mass times velocity at point B squared, plus the potential energy there, which is Q times the potential at point B. And this should remind you of problems you did in the previous class. It's kind of the same thing. The only thing that's changing is how we write the potential energy. We're not using one of the potential energies you had previously. So we're solving here for the velocity at point B, which just means some algebra must be done, right? So let's see, 1/2 mass velocity A squared plus Q VA minus Q VB. And we're going to have to take that whole thing and multiply by 2 and divide by the mass and take the square root. There we go. Did all the algebra in one fell swoop. No? Did I mess up?
Yeah, VB, the one inside, isn't supposed to be there.
VB isn't supposed to be there.
That's supposed to be divided by Q.
Let's see, I've got this one plus that one, and then I'm going to subtract this one over on this side, and then multiply this by 2, divide by mass, take a square root. I think it's good.
But you don't have the VB. How will you plug it in?
Don't have VB.
The one inside. Next
This
to
one?
the- Yeah.
Oh, we do have that one though. It's 620.
Oh, it's-
That's the potential at point B.
oh,
So let's plug these in and make sure that we're all on the same page as far as what the numbers are. So the mass, they said, was 1.2 times 10 to the minus 4 kilograms. The velocity at A is 3.9, so it's 3.9 squared, plus, and let's be a little careful here, that's a negative charge, so minus 4.1 times 10 to the minus 6, to convert that to coulombs, times the potential at point A, which was 190, minus a minus 4.1 times 10 to the minus 6, times 620. Make sure we get all of that inside those brackets and divide by the mass, which is 1.2 times 10 to the minus 4. All of that equals the velocity at point B. And it should be 6.68 meters per second. It's sped up. Think about that for a second. It's going faster when it gets to point B. Does that make sense? Like, I'm not sure if it makes sense. Is it supposed to make sense? It should make sense. Tell me this, based on these potentials, higher potential, lower potential, which direction is the electric field between points A and B? It's up, down, left, right, in, out, sideways. Which direction does the electric field point? Electric field points from high potential to low potential. High potential to low potential. So that means the electric field is going this way. Electric field is going that way. So does it make sense that a negative charge would speed up as it goes the opposite direction? Yes, right? A positive charge would feel a force in the direction of the electric field, which means that if it had a velocity here, it would feel a force and go faster, okay? It like wants to go in the direction from higher to lower potential. A negative charge is going to do exactly the opposite. A negative charge feels a force the opposite direction, okay? So if it has a certain velocity here, well, it makes sense that going against the electric field, it's going to go faster because it feels a force that way, okay? And notice, in case you missed it right here at the top where you can't really see, that is a negative charge that we're dealing with, okay? So if we dropped a positive charge there, we should have found a lower velocity here, and you could try that. Just put in positive values for the exact same charge, and you should end up with a velocity that decreases instead. So you could try that for your own instruction if you wanted to, okay? Now we're going to get to what I really want to get to, all right? We talked about a few different things over the last few chapters. In the first chapter we covered, we dealt with the electric force, and at some point in that chapter we wrote out an equation for the electric force that's created by a point charge. Does anybody remember what that equation looked like? Or the equation, I guess it was between two point charges. The electric force. I think I heard it out there. We could write it as K, Q1, Q2, good, over R squared, right? That is for a point charge, or for dealing with point charges, 2 point charges. Both of them feel the same force on each other, okay? Then in the next chapter, we found the electric field created by a point charge. Does anybody remember that one? K times what? It's just Q over R squared. Okay, that's been our sequence so far. Each chapter has had one of these, sort of. It's like force, we dealt with that. Then we moved to electric field, again, just dealing with point charges. Now you can see there at the top, we're going to look at the electric potential that's created or comes from a point charge. So we can write that as V. And it turns out, if you look back at our last lecture, we did a bunch of calculus and actually found this answer already. So I'm not going to go through this again. We just didn't specify it at the time. It's simply KQ over R. So we get rid of that extra R that's in the denominator. And again, this is potential that is created by a point charge. I don't want you to forget, though, the key thing about potential is that it is a scalar. And you will find when we do some problems here in just a minute that it makes calculations so much easier. Like delightfully easier. Like some of you might just like swoon with delight. You're going to be like, this is fantastic. Why can't we do it this way all the time? Much of the time you can. because we have connections between potential and electric field. So if given the option, and I ask you to find the electric field, you can be like, ooh, if I know how to do that by finding the potential first, my life is a lot easier, okay? So this is a scalar, which brings me to the first diagram, and what I put up there, like I didn't actually want to talk about, we did that already, which is these two diagrams, and I need a moment to explain what we're looking at, okay? Notice at the top, it still says electric potential from a point charge. We are still using this equation, okay? So a couple of different things about that equation. K is just a constant, we know that, it's 9 times 10 to the 9th. Q can be positive or negative, which means I can have a positive or negative value for the scalar potential. R, being in the denominator, is just telling me that, well, it's going to get weaker. There's less potential as I get farther away from the charge. And it falls off according to 1 over R. You could draw a 1 over R curve, okay? So looking here on the right, we've got a graph of the electric potential in the region of space near a positive charge, and then we've got the same thing in a region of space near a negative charge. Now the way these diagrams are drawn, I both like them and dislike them because if you notice the axes, like stare at that for just a second, it's like where is X and Y exactly and where is the charge? I understand it's confusing. So you can see that first of all, 0 on the x-axis is here in the middle, and then you got to go all the way up to the top to figure out where 0 on the y-axis is. Ugh. Yeah, it's a mess. The origin actually sits kind of like down here in this bottom plane. It's trying to tell you that like this is one axis and another axis looks sort of something like that. Okay? So y is, positive y is this way, positive x is that way, but my xy plane is sort of in the base of that cube. Does everybody see that? Maybe a little bit, okay? The positive charge that they're talking about is at the origin. So right there we have positive q. It's sitting at the origin. All of this other stuff that's graphed around it are just the numbers for the electric potential, and they're graphed on the z-axis, okay? So essentially what someone did was take this equation and just basically plug in a single charge of maybe, they just put in like a 1, and then put in something like the constant for k, and then just went to every coordinate r and decided to calculate the potential and see what that is. Clearly that would be a lot of work, so someone just generated the whole thing on a computer, okay? When you do that, well, it makes sense that if I put in very, very small values for r, I get very large values for potential, okay? And you can see on this diagram, anywhere when I'm really, really close to 0, 0, notice what the potential is doing. It's basically going to infinity as I get really, really close to that charge. All right. If I get farther and farther away from the charge, well, according to this, if I get farther away, the potential is going to drop and it gets really weak as I get farther away. Okay. So this is a way of sort of visualizing what the potential looks like. It's positive and big near a positive charge. It gets smaller as you get farther away, but it's positive everywhere in the region of space around it. Okay? Let me pause there for a second, take your question.
So is this only for a point charge? It's not for that scenario where we have the 2 plates and we put something in?
Nope. This is just a single point charge that's sitting somewhere in the XY plane, just all over. All right? We could graph something similarly in 3 dimensions, but boy, that would be a bear to try to look at. Right? We would need a video and be able to like rotate it and stuff to try to look at that, okay? These are just the values at different x, y positions in that same plane. Now I want to zoom in on this just a little bit. There's some other lines here that are actually instructive. Whee! All kinds of fun, okay? These green ones, these circles that go around, we're gonna deal with those later in today's lecture. So just keep in mind, those green lines are there for a reason, okay? These purple ones that are pointing out, they actually represent something. Let's draw them in here. Oh, what color to go with? something that contrasts with it a little bit. Oh, I shouldn't use green because that's just going to confuse. This line represents, believe it or not, the electric field. Now let's step back and think about that a little bit. All of these lines around here represent the electric field around that charge. Imagine something with me, if you will. Take this diagram and let's just flip the whole thing towards you so you're like looking down on top of this cone shape that's there. Okay? What are you going to see if you look down on top of it? See something that looks like this. Right? I would just see a positive y and a positive x. I would see my positive point charge in the middle, and I would see all of these lines sort of going out from it in all directions. I wouldn't see that curve. I would just see all these lines just going radially outward, right? That's what we learned the electric field for a positive charge looked like. Agreed? Okay, so that's represented here on this diagram. What is being added to that is the slope quantity and how it relates back to the potential. Remember, we said that the electric field is the negative slope of the potential. Look at the diagram. Like, what if we kind of went like, you know, like right here and looked at one of these lines that I said is the electric field? Well, that has a slope, right? The potential values, the actual numbers for potential here are changing and they're dropping rapidly, okay? They're also going down. They're becoming less. I could go right on this line, right on the side of this curve and find the slope. It would be a negative slope, and that negative slope is how quickly the potential is changing. That is the electric field. Do you see how these things kind of tie together just a little bit? I know it's a lot, but if you can like grasp this slide, it explains a whole lot of everything that we've been doing in this chapter and in the last, okay? Let me represent this one more way. Think about what electric field and potential mean. They're sort of like two sides of the same coin. One is a vector way of describing it, one is a scalar way of describing it. For an electric field, we say that that is the direction a positive charge would get pushed, okay? So if I'm dealing with a positive charge being near another positive charge, I know it gets shoved away. Well, that's what these electric field lines are telling me. They're saying, like, put a positive charge there anywhere, it'll get shoved away. I can also represent that as a potential. Positive charges want to go from high potential to low potential. So what if we sort of relate this back and pretend like this is a physical hill and there's gravity? You could imagine if I put something right here and I was pretending that this whole thing is related to gravity, what's it going to do? Whee, right? It's like going to ride that slope down and be pushed away. Is anything really there that's like a hill? No. But you can think of it sort of in those terms. It wants to ride that potential from a high potential and go over to where there's a lower potential. That's what the object wants to do. Just like something in gravity, it wants to go from a high potential down to a lower potential. It's just that this is kind of the only way we can visualize it, because just like I can't see, like there's no like potential that's here. It's the same thing when I'm dealing with the region around charges. There's nothing physical there, but there is an impact. There's a presence that makes things want to go from high potential to low potential, okay? Do you see the electric field, the electric potential, and how that slope there connects the two together? If you understand it like half, that's pretty good at this point. You're gonna have to sit with it a little bit maybe to kind of absorb it a little more. Let me slide over to this one. We'll talk through it one more time, and then hopefully everything kind of comes together. So this time we're near a negative charge. What does a positive charge want to do if you put it near a negative charge? Right? It gets drawn to the negative charge. Okay? So in this particular diagram, this time, for whatever reason, they have decided that the X and Y axis are up here in the top part. I'm sorry that those are backwards like that, but maybe you get the idea. So this is positive Y, this is positive X, and the origin sits right there in the top box of that cube. Okay? So this is where there is a negative charge. It's sitting right there in the XY plane, which is at the top. Okay? So you can imagine that if I were to bring a positive charge somewhere nearby, what if all of a sudden it's like, oh, a little positive charge kind of wanders into this region? Like, as long as it's like way over here somewhere, like, that's fine. You can just set it there. It's no big deal. If it gets too close to that negative charge, though, the negative charge is going to take over. And you can sort of see that represented by the way they've drawn the slope, right? If this positive charge gets a little too close, it gets sucked into the hole, okay? That's representing it being pulled in by the electric force that we draw as an electric field, and you can see that effect drawn in the potential as a potential hole, okay? Yeah.
So is this scenario synonymous with like gravity?
Same kind of idea. We can draw pictures like this for gravitational potential as well.
But it would only be the one on the right because there's no repulsion.
Exactly.
Okay.
Yep. And maybe you've seen diagrams like this with like black holes and things kind of like that. It's the same exact concept. The math is all basically identical. So if we look at this diagram, again, you see these lines. Now the electric field, remember, points inward for a negative charge, so that any positive charge that comes nearby gets drawn toward it, okay? Notice also that all of these values of potential, look at this vertical axis, they're all negative, right? It's a scalar. If there's a negative charge, it creates a negative potential everywhere around it. Who's got questions? How much fun is that? This is like the best slide we've done all semester so far. Yeah.
Do the actual lengths of E determine its magnitude?
Yes, but those aren't really represented here. So if we were to like carefully draw the electric field vectors, they would be very long close to the charge and shorter as we get farther away. None of that's really drawn there. Who else? We're not really done with this idea yet, okay? What I want to do now is, like, on the next slide, we're going to do an electric potential calculation of our own, okay? I'm going to show you how easy this can be. I'm going to ask you a few questions. We may skip that for today because I want to get to these diagrams as well. You might start to recognize that they, in some ways, look familiar to what we just did, okay? So let me start with this. 2 point charges. Oh, look, it's actually all on the screen this time. Notice the first one is positive, the second one is negative, and they are placed 1/10 of a meter apart. You can see that drawn here in the diagram. We've got a positive charge Q1, and we've got a negative charge Q2. Point A is right in the middle between them. Point B is in that position kind of closer to Q2 than it is to Q1. We are going to try to find the electric potential at point A and at point B, okay? So let me scroll forward to make sure I have all the right answers in front of me because that's just nice to have, okay? If I want to find the electric potential at point A that's coming from point charges, all I have to do is find the electric potential from charge 1 and add it to the electric potential from charge 2. No vector considerations at all. Yay. Be happy. No vector considerations at all. Yay. That's better than nothing. no vector to worry about at all.
Yay.
None. No vectors. Yes, exactly. If we tried to do this, and I'm going to show you in just a second, and tried to find the electric field here, you're going to be sitting here working on it for a little while, okay? Because there's like no symmetry where things cancel out or anything. Like you just have to like brute force your way through the entire problem. So if I want to find the total potential, we're just going to write K times Q1 over R1 plus K times Q2 over R2. D2. It's weird how that happens. So the K's are the same. I'm going to go ahead and factor those out just to simplify the math a little bit. And we've got Q1 over R1 plus Q2 over R2. And let's plug the numbers in. And then we're done. So K is 9 times 10 to the 9th. Q1 is positive, and notice it's listed as nanocoulombs. I need to convert that to coulombs, so it's going to be 2.3 times 10 to the minus 9. And R1 is just the distance we are away from Q1, and you can see that that's 0.05 meters. Q2 is negative, so I'm going to go ahead and write the negative sign there. And then it's 6 nanocoulombs, so 6 times 10 to the minus 9, and it's 0.05 away. So the total potential at point A is just that, and interestingly and weirdly enough, it's negative 666 volts. You gotta love that, right? Yes. 1,000 times yes. Remember how we found the electric field? Yeah, like if I want to find the electric field at point A, like first of all, I have to be like, okay, let's say there's a positive charge there. Which way would it get pushed? It would get pushed this way. So E1 goes here. And a positive charge would be drawn to the other one, so I would have E2, and it would go that way. So I would have to consider the fact they're pointing in the same direction, and then yes, I could use K Q1 over R1 squared plus K Q2 over R2 squared, and that would be fine because they're pointing in the same direction. That would give me a total electric field at point A. And we would find that it points, we'll say to the right. So that one wouldn't be too bad for finding the electric field. Okay, what about the electric potential and electric field at point B? Well, that's not terribly bad either. So it's just going to be V1 plus V2. So once again, this is going to work out to be K times Q1 over R1 plus Q2 over R2. Do you hear that? Like, you know, it just kind of like, you hear R2 and you can't help but hear D2. It's just one of those things. You know, I don't know what the deal is. So let's see. Some of the numbers have changed, but otherwise everything is fine. So this is 9 times 10 to the 9th. Q1 is still 2.3 times 10 to the minus 9. Our distance here has changed. It's now 0.08 away. Minus 6 times 10 to the minus 9. And this distance is 0.06, just looking at the diagram. For this, you should get negative 641 volts. Again, that's not too bad, right? Imagine what you would have to do with electric field, though. Yeah, I don't want to. You know, we're going to. I don't want to, but we're going to, okay? So imagine there was a positive charge there. Well, it's going to get pushed away from Q1, so I'd have an electric field that points that way. And it would get drawn toward Q2, so I would have an electric field that goes that way. And then I'd have to find those angles and break them into components, and it'd be terrible. Okay, you should be able to do that though, in case I ask you how to do it next Thursday. It would be a really nice problem to say like, hey, here's some charges. Find the electric force, the electric field, the electric potential. Like that kind of ties everything together. That should be the whole exam. That'd be fantastic. Hello, get my picture taken. And nice to see you. Yeah, this is my work. Fantastic. Yeah. I'm wondering at this point, like how many pictures are out there with me like this and a screen behind me? There's got to be a billion. Sadly, no one's tagging me on Instagram. You know, I don't know what's out there. Who knows? But I bet I look terrible in all of them, right? Like I should know. I should just immediately be like, yeah, but no one ever gives me the chance. So, electric potential at point A and point B, that's how it's done. That is wonderful, don't you think? You can do this. Yes? Oh, you can do it. You'll be fine. So moving on. I want to skip a few slides to make sure that we cover the material, or at least the focus on the material, and then we can always come back and answer a few of these questions. So let's take a look at these diagrams. These diagrams introduce those green circular lines that were on the other one. Notice these are color matched to what we had before with the big, you know, the hole and the peak. We had the purple lines that were representing the electric field, and there were these green circles that I said we'd come back to later. These are known as equipotential lines. And equipotential lines is really just a simple, well, not a simple, but a complicated word to describe locations where the potential is exactly the same. So if you go back and look at our equation, V is equal to K, Q over R, well, if I'm dealing with a certain charge, the potential will be the same if R is the same. Right? If you're the same distance away from a charge, everywhere that I'm the same distance away, I'm going to get the exact same value for the potential. So that's what these lines are trying to show. Notice they're circles. If I'm around a positive charge, well, if I go out to some distance and I go in any direction that distance away, this equation is going to give me the exact same answer for the electric potential. Or I can go to some other distance away, and everywhere on that circle, I'm the same distance r away from the charge, so I get the same value for the potential. Okay? This might remind you of another type of map or drawing that perhaps you've seen, especially if you like to hike, and maybe if you take hiking seriously, which I don't by any stretch of the imagination, because walking, and especially walking up and down hills, is exhausting. There's a picture of me that I like a lot from about 5 years ago, where my wife and I were going to go for a walk. Well, the walk started at the donut shop, right? So there's me on the trail, like, let's walk, and I've got a donut, and we're heading down the trail, and everything was fantastic. It should have also ended at the donut shop. We needed to go around a closed loop and start into the same place, and life would have been happier. But, you know, my wife got me to walk by giving me a donut. It's like, I might as well be a puppy. That's really kind of what happened. It's like, you know, Nathan, come walk. I got a donut. You know, I eat a donut and everything's happy. So a topographical map is a map that shows us something about gravity and where gravitational potential is the same. So maybe there's a map of like a hill or something. Let me go over here. And maybe it's a hill that looks like this. It's like, whee, there's a very sharp hill. And then maybe over on this side, it's, you know, kind of slopes down something like this. Okay? And this is a side view of that hill. What am I writing? I don't know anymore. Side view. Well, a topographical map shows us something about elevation by relating it to gravitational potential. So you might see something that kind of looks like this. I don't know, maybe there's like a circle like this. And then over on this side, it kind of does something like this. And then these are like really close together. And maybe it looks kind of something like that from the top view. You've seen this, right? Okay. That's trying to tell you something about potential, and these lines are equipotential lines, even though they don't call them that. Okay? Each one of these lines means that there is no change in potential. It means there's no change in altitude. So in other words, if you're like me and you want to go on a hike, right, you want to look at one of these maps and figure out where one of these lines is located and stay on it. Okay? Because if you just pick this line and go around this way, assuming there's a path that follows that, you never go up or down. You stay nice and easy level, and everything is fine. Okay? What you don't want to do is like go perpendicular to these lines. See, this indicates that your slope or your potential is changing rapidly. Okay? The way that they draw these lines is what they're saying is that every separation is the same change in elevation. So maybe a separation between lines here represents, I don't know, 100 feet. Well, this means over a very short distance, it's like 100 feet up, another 100 feet up, another 100 feet up. Oh, I'm at the top. And I had to do that in a very short horizontal distance. This would mean like from here to here is 100 feet up. Ah, that seems a little better. And another 100 feet up, and another 100 feet up, and so forth. Okay? So this is an easier slope going here than it is there because the potential isn't changing as fast. All right? So a topographical map is really what we're looking at here. It's just the topography isn't elevation changes, it's potential, and specifically electrical potential changes. Now, think about this and think back to that first three-dimensional diagram we looked at. Remember I said look down on the top of it? This is the top view of that diagram. You can actually imagine this as like a peak that's coming out towards you, okay? The positive charge sits near the middle of that peak because that's where the potential is the greatest, and then the potential falls off as you get farther away. Notice they've actually drawn in the electric field lines this time and say that they push away. Also, notice the way these equipotential lines are positioned. They're really close together when I'm close to the charge because the slope is falling off rapidly. And as I get farther away, things are getting flatter. Okay? Those diagrams on the other page and these diagrams work together. The colors are the same and everything to help you understand potential and electric field. Let's see, what else should we say about this? Oh, well, of course, also, like, where do you want to hike around an electric charge? Stay on one of these green lines because the potential doesn't change. You don't have to fight with or against the electric field by going up or down, okay? There are some more complicated examples here. So here they've just decided to draw a similar thing, but for two positive charges that are close to each other. It's almost like you could look at this and imagine these are two peaks of a mountain, okay? It's like we took this and put another one right next to it. So this is going up to a peak here, and then maybe it doesn't level out all the way in the middle, but there's another peak that's there, okay? Again, well, you can kind of see what the equipotentials are looking like, and also the electric field lines tell me which direction a positive charge would get pushed. But I like the one that's over here on the right. One positive and one negative. One positive and one negative. Think about what that means if I were to graph this as three-dimensional potential, okay? Positive values and negative values. Remember, near a positive charge, this is like a peak that's coming out this way, right? It's like a mountain in this direction. A negative is a peak in the negative direction. It gives me negative values of potential. So it's like I've got a mountain coming out here, and on the other side, we've got a mountain that's more like an inverse mountain, right? It's like a pit or a hole that's going the other way. Can everybody see that? Yes, you can visualize it. There we go, okay? Let's make sure that this makes sense. Imagine what would happen if I take a positive charge and put it near this positive charge. Remember, it's sitting all the way at the top of this positive potential mountain. Well, of course, it's going to like be pushed away, kind of like it rolls down the potential mountain. And then, well, there's a pit right next door. It's just going to keep on going and roll right into that other pit, right? Well, that's reflected in the electric field. If I put a positive charge here, it's going to get pushed away from this positive charge and end up stuck next to this negative charge. The electric field seems to agree with what we see in the potential map. Whew, it's a lot of stuff. Are you feeling okay? Are you feeling better than you did before? Does this stuff kind of help a little bit? Maybe it ties it together. I don't know. How's our time? Doing pretty good. Excellent. Okay, so let's move forward here once again. Yay! We're actually not going to do this slide. I changed my mind. And yeah, we're not going to do, no, we are already going to do that slide. Let me leave that in there. But we're going to do that next time. Let's see. So I want to give you guys a problem to work before we leave today. And then we're going to go back and fill in a few of these gaps. You've got basically the material that you have to know for the exam. The other stuff is just some clarification, a few details, etc. But we can finish that up easily on Thursday. Because I want to give you some practice problem on the potential. And let's see, let's just put a slide in here somewhere, and I will write you out a problem. So go ahead and find someone. The potential at point B, which is this point, is supposed to be right on the y-axis. The same two charges at the bottom. What do you think it is?
0.
All at once. 0, because I'm in the exact same distance from both of the charges. So both of those terms on the previous slide are going to be equal, just one positive and one negative. So at that point, I get 0 potential. Now you can imagine for a situation like this where I have two charges, I could ask you to find the potential at any point, right? I could say, hey, what's the potential right here? What's the potential right there? What's the potential right here? What's the potential right there? Right here, I could sign like 1,000 million problems, right? If I wanted to, like practice if you want to. Just pick some random place at some distance from the two charges and make sure you understand how to calculate the potential. You should also be able to take two charges and find the force on a third charge somewhere else. You should be able to take two charges and find the electric field at some other point. These are all things that we've done in these first 3 chapters. Electric field, electric force, and potential from point charges, okay? We're gonna do an example later that's just like that, all right? So moving on, 4 point charges are arranged at the corners of a square. The 2 left ones are negative, the 2 right ones are positive. Find the electric field and the potential at the middle on that black dot. And you can see our answers are not exact. It's just 0 or not 0 for both of them. The electric field and the potential at the center. What happened here exactly? I feel like something occurred here today that like either someone was in trouble and they were forced to sit with this little desk chair thing. Maybe someone had lunch here. I don't know. I kind of want to lecture from this position for the rest of the class. There we go. This is kind of fun. Y'all think about that while I'm over here doing my own thing. Can't help but want to turn around. Let's take them one at a time. Potential at the center of the square. 0 or not? That's good. Nice work. So the 2 answers are either 0 or not. So say the word 0 or not, whatever your answer is. Go.
0.
It sounded more like 0, right? So our answers are either that one or that one. And again, that point at the middle is equidistant from 2 positive and 2 negative charges. It should add to give me 0. But what about the electric field? Imagine what would happen if I drop a positive charge at that point. Will it feel a force or will it not? Sure seems like it might feel a force, right? You can imagine it's going to be repelled by both of these and it's going to be drawn to both of those, right? It's going to feel a force toward the left, at least roughly speaking. So the potential here is 0, but the electric field there has some value that points to the left because I know a positive charge would feel a force in that direction. So our overall answer is this. There is an electric field at that point, but there's no potential. How's that possible? One second, I'm going to change slides and see if there's something here that might help. Going back to, which one? Maybe this one would help. take a look at that right diagram. Remember we talked about this being like a big mountain that's coming out? And over here, this negative charge represents a negative, like a hole of potential, right? Well, right in the middle, you would have a potential of 0. Agreed? It's kind of like, that's kind of like ground level. Here I have a mountain, here I have a valley. Right in the middle is like exactly 0, not positive or negative. But right in the middle, there is an electric field because something's going to want to go from high down to the low point, okay? There's still an electric field in the middle because there's a slope in the potential, where the negative slope of the potential is the electric field. So you can almost imagine this, like if I were to flip this sort of sideways like this, like it's going something like this. I'm going from one peak in the potential that's positive down to a valley that's negative. There's a point in the middle that's 0, but the potential is changing and has a slope through that point. If there is a slope and the potential is changing, well then there is an electric field, okay? If you're trying to think about how the electric field and potential relate, like try to get some of this 3-dimensional figure stuff in your head. Try to relate it back to that. Imagine potential as these mountains and valleys. And I think it helps a little bit trying to understand the electric field. Maybe it does, maybe it doesn't, who knows? So back to this one. Electric field is not 0, it exists. The potential though is 0. Yeah.
Is the force being exerted by both the positive charge and the negative charge the same?
The force being exerted by both,
Like if we see it in 2 separate systems.
yes, but it's also dependent on the charge that's feeling the force. So a given charge would feel the same force from both an equal positive and negative charge, just in opposite directions. Yep. Okay. Yeah.
Even though that is like neutral, since they're both like giving off the same, it's still like the forces they feel. That's why we have to answer it as like not equal to 0.
As far as in this problem? Yeah, if there is a force, then there is an electric field. And there will be a force if you can imagine repulsion and attraction being something that's happening at that point. Okay? There is one new thing here on this slide. One new thing. There's going to be something a little new later, but actually we've already kind of talked about it. So electric potential from point charges is what we just finished. We just used KQ over R if I have a point charge. But sometimes I have too many charges to count, just like before, and we express that as a distribution of charges, just imagining there's like infinite numbers of little charges that are all sort of packed together. We're going to do something kind of like that with a bunch of charges distributed in a ring, okay? And again, it's going to work the exact same way. We're going to imagine there's a little bit of charge in a little bit of that ring, and then we're going to see what the potential is over at some point from that little bit, and then add up the contribution from all the little pieces of the ring that each contain some charge. The thing is, this time I'm not going to think about like, oh, there's like a vector and some of the components maybe cancel out and some don't. I don't have to think about that. I literally get to just use the integral to just add it up because it's a scalar, which makes life a lot easier. So we're going to express this in an integral form to allow us to do this. So I could write V as K, or 1 over 4 pi epsilon naught, times the integral of dq over R. And we'll call this the integral form of the exact same equation. It's just now we're breaking up the charge into little segments of charge. So if I want to use that equation with this example, this ring of charge, watch how quickly we arrive at an answer. It's kind of ridiculous. So first of all, this R that's there, if I'm trying to find the potential at this point that's like some distance x right away from the middle of the ring, well then over to any point on the ring, the distance R is this hypotenuse. And that value is constant, okay? No matter where I go on this ring, The length of that hypotenuse is exactly the same, and it's the square root of x squared plus r squared, the radius. It's going to be a constant value though. So I can go ahead and pull that out of the integral. So I've got k over r dq. And then we can express r as what they have there, the square root of x squared plus r squared. So I've got k over the square root of x squared plus r squared, integral dq. And we're basically done, believe it or not. If I'm just doing the integral of all the little pieces of charge, what is all the little pieces added up? It's just q. So this is kq over the square root of x squared plus r squared. Wow, that was fast. That happened ridiculously fast. kq over that distance. So what happens if I get very far away? Let me just see what happens. Very far away from this. In other words, if x is much greater than much. I can do this all day. You get the idea. Much greater than the radius. So instead of looking at some distance x, we're just going to let the x be way over here somewhere and try to find out what that would be. Well, I can take a look at this equation and say that now x squared is going to dwarf r squared by comparison. So essentially the r squared isn't even there anymore, and I just have the square root of x squared, which means that my potential becomes kq over what? Just x, right? Where x is the distance away. Well, that looks a whole lot like this. We're just using x instead of r, but both are just a distance, which means if I get far enough away, this ring of charge looks like a point charge. And that fits, right? If something's a disk and I get far enough away from that, all I see is a point, okay? So this equation seems to fit with what we would expect from a great distance. And we're done with that. That wasn't too bad compared to some of the other calculus examples we've had, I don't think, okay? So let's jump over here, and I've got some other questions to give you. We talked about these equipotential lines and surfaces, and I drew this diagram, but we didn't actually talk about the problem that's sitting on that page. At which point, 1, 2, 3, 4, or 5 is an option, would the potential be equal to 0? Notice they drew a line down through here. This is an equipotential line. An equipotential line is a line on which all the potentials are the same, and all of those are equidistant from both the positive and the negative charge, which means all of them are going to have potential equal to 0, okay? What about this one? Which 2 points have the same potential? Don't think about this for too long. Which 2 lie on an equipotential line together? Looks a whole lot like C and E are both on this equipotential line that goes around closest. So our answer there is number 4. Okay, equipotential line once again. I already decided to skip the electric dipole stuff. Turns out we don't really need it for this class, so I'm going to jump over that, which brings me to the last 2 slides of this chapter, and then we're going to do some review stuff, all right? So electric field from electric potential. In other words, if you have the electric potential, which remember is a scalar, which remember is easier to calculate, we can go from there and calculate an electric field. If you have the potential, it's possible to go backwards and find the electric field without having to do all of the vector work. So you might remember we had an equation that kind of Let's see. It sort of looked like this. We said it was the change in potential over D. We had an equation that looks like that connected the two. We used that to say that the electric field is the negative slope of the potential. The electric field is the negative slope of the potential, and we used that idea together with our three-dimensional diagrams to see how the potential is changing, and it had all of those little pink, purpley sort of lines on there that we said represented the electric field, and it was literally the slope of the potential. Well, I can re-express this equation just a little bit and write it as E sub L, where L is just some arbitrary direction. In other words, it's one of the components of the electric field. It's just instead of saying X, Y, or Z, I'm just saying that way. Or maybe it's this way. I don't know. I'm not picking one of the directions. So I'm speaking really generally here. The component of the electric field in some arbitrary direction L is equal to the derivative of the potential with respect to that particular position. So again, we're dealing with the negative slope or the negative rate of change of potential in that particular direction, that L direction. So let's write down a couple of different things about what this means. First of all, this is mathematically known as the gradient of the potential in the L direction, in case you're familiar with that terminology. And it is the negative rate of change of the potential in the L direction. The negative rate of change of potential, which is defined as the gradient of the potential. So to put this in terminology that maybe you like a little bit better, we could find the X component of the electric field and the Y component and even a Z component if we had three-dimensional situations. We're finding the components of the electric field vector. We can use this particular equation in all three directions. So instead of some arbitrary L direction, we can write this in terms of X, Y, and Z, which we're a little bit more familiar with. Except if it's a function of maybe X, Y, and Z, I have to rewrite that as partial derivatives. So this would be the negative, the partial derivative of the potential with respect to X, and the partial derivative of potential with respect to Y, and negative the partial with respect to Z. And you might remember or may not that when you're doing a partial derivative, it just means you're going to take the derivative with respect to that one variable and hold the other ones constant. So your equation might have X's and Y's and Z's in there. Just pretend when we're dealing with X that anything with Y and Z is just a constant value, okay? And you're not having to worry about that at all. And let me do a quick example of this for you, okay? So let's say that we had something like this. The potential as a function of X, Y, and Z. Meaning maybe we have an equation that we could plug into the computer and get it to graph one of these pretty three-dimensional things that tells us what the potential is at every point in space. And maybe that function looks something like this. 2x squared plus 8y squared z, and who in the world knows what this looks like, plus 2z squared. Maybe you plug that in and get it to graph that in 3 dimensions for you. If we wanted to find Ex, well then we look at that function and again take the partial derivative of the whole thing with a negative sign with respect to x, making sure that anything that has a y and a z, we just pretend those are constant. So when I take that derivative, that's just a 0. We don't have to worry about it at all. So for this one, the derivative is going to be 4x, and we would throw a negative sign in front of it. So EX is going to be minus 4x. That is the component of the electric field in the x direction. And EY, we could do a similar thing. In this particular case, well, I have an x here. This one's going to be 0. We have a z over here, so this one's going to be 0. And we can pretend that the z in the middle is, again, just a constant. So in this case, we would have minus 16, and we could put the z in front to pretend it's a constant, times y, minus 16y. And the z component of the electric field would be expressed as minus 8y squared. The first term is constant, so it's just 0. This one, we're pretending that the y squared is a constant, so everything is constant out in front of the z, so that's just minus 8y squared. And the last one would be minus 4z. Those would be the equations for the components of the electric field at all the points in x, y, and z space, okay? So you can do a lot of work in 3 dimensions if you know the function, and you can like very, very quickly get to the answers. And of course, if you wanted to say like, oh, well, what is the electric field vector at this point? Like maybe at the ordered pair 1, 1, 1, x equals 1, y equals 1, z equals 1. We'll just plug the numbers in, and it'll tell you what the 3 components of the electric field are at that point. And you could do that for all the points, and all of a sudden you have a nice, pretty graph of everything that's represented once again, okay? Any questions about that one? Before we do the last slide, which I have nothing hardly to say. It's just a different unit that you may sometimes see, and I want to make sure that you're aware of it. And it is the electron volt. 1 eV, the electron volt, is equal to 1.6 times 10 to the minus 19 joules. It turns out that a joule of energy, and we were talking at the start of the chapter about potential energies and dealing with that, a joule is really, really, really big. And we're dealing with things that are charged like electrons and protons. So often, instead of having to deal with 10 to the minus 19 on everything, it's just easier to re-express really small energies in terms of a different unit, like electron volts. It turns out that the electron volt is defined as the energy required to move a charge equal to the elementary charge, and keep in mind that's 1.6 times 10 to the minus 19 coulombs, through a potential difference equal to 1 volt. A, B, so in other words, if I had an electron and it was at one point and I wanted to push that electron over to another point that had a different potential that was 1 volt in difference, 1 electron volt is how much energy would be required to do that amount of work. So often when we're dealing with atomic things, electron volts are used for energies instead of joules, just because it's a little bit easier to work with, and some of your homework problems could have things in electron volts, and just want to make sure you're aware of that, okay? We're done with all of this stuff for our test 1 week from today. So I want to do 2 problems by means of review. And let me just say in advance that if you've been working the homework, you might find it to be a little bit familiar. The numbers may have changed to protect the innocent. I don't know. But the problems may seem familiar. So if you've been working on it and getting stuck, you're about to get some help. If you've been working on it and got the right answer on problems that look like these, well, consider it just a review. Just sit back and enjoy it. If you haven't been working on the homework, get out. that's sad. It makes me sad, and you should be sad because you're going to be sad next Thursday. You need to be working on the homework, all right? So if you haven't been working on it at all, just take this as a little bit of a gift in the sense that, like, oh, you're behind, you need a little help at this point. So don't just take the answers, make sure you understand all that I'm about to say. So let's go over and insert a new slide right there, right here at the end. Insert page, beautiful. Don't know why it never allows me though to insert a landscape page that matches everything else. And that upsets me, but one of these days I will sort out why the software will not let me do what I want to do. So let's see. Let me open up these files for whatever reason.